Hello everyone, hello students. I hope you are doing very well. Great. So I am Brijesh Kumar and today we are going to start day 24 and of our JEE 45 days crash course. Okay. So let's begin with the session. So you can see here what is the syllabus for JEE-Main 2024 for P block elements. So what are the topics included? You can see group 13 to group 18 elements are included in P block. Okay, so what we will be covering: general introduction, electronic configuration and general trends in physical and chemical properties of elements across the periods and down the groups, okay, in a periodic table, and unique behavior of the first element in each group. Okay, so today's topic is group 13 and 14 elements today we are covering. So let's begin with the session. So you can see here the P block elements from group 13 to group 18, 2 to 3 questions are there. Okay, can be asked in JEE-Main exams. So you can see what are the topics to be covered today. You can see electronic configuration of P block elements. Okay, what is the electronic configuration or general electronic configuration of P block elements we will be covering today. Periodicity in properties of P block elements. Group 13 elements, boron family we will be covering, some important reactions of boron, and then unique behavior of the boron element in each group. Okay, and boron element in its group. Okay, boron element in its group. Group 14 elements, carbon family, and some important reactions of carbon, some important questions for JEE exams, and unique behavior of the carbon element in its group. So you can see here first of all the periodic table. You can see the periodic table of the elements. In this periodic table we have 118 elements. Okay, so you know very well 118 elements have been discovered so far, and out of these 118 elements you can see from group 13 to group 18, group 13 to group 18 elements are included in P block. Actually this periodic table, you know very well, this periodic table, actually this is the periodic table, and bottom two rows are also there. Okay, this periodic table actually divided into four block: S block, P block, D block, and these two rows are F block. Okay, so today we are covering only P block, and in P block we are covering only group 13 and group 14. Okay, so let's begin. So in this P block, group 13, 14, 15, 16, 17 and 18, so total 6 groups are there. Okay, so today we are covering two groups, and that means two family, boron family and carbon family, and in the next session we will be covering the rest four groups. These are the rest four groups: 15th group, 16th group, and 17th and 18th group. Okay, so you can see here the periodic table. You can see boron, aluminium, gallium, indium, thallium, these are in group 13, that means in the boron family. Okay, what is the general electronic configuration for P block elements? The general electronic configuration for P block elements is ns2 np126, because the last shell electron is entering into the P block or P subshell. That's why these elements are what are divided into or are categorized into P block elements. Okay, similarly you can see group 14. Group 14 is carbon family: carbon, silicon, germanium, tin and lead. Okay, and these rest are what? Radioactive elements. These are radioactive elements. Okay, so you can see carbon, silicon, germanium, tin and lead. The general electronic configuration for the entire P block is ns2 np126, but for group 13 the general electronic configuration I want to tell here, for group 13 the entire P block general electronic configuration is ns2np126. Now for group 13 this is ns2np1, where n belongs to the number period number, right? And group 14 ns2np2, group 15 ns2np3, group 16 ns2np4, group 17 ns2np5, ns2np4, ns2np5, and group 18 ns2np6, ns2np6. So these are the groups, and this is the general electronic configuration of each group or each family, right? Okay, you can see this group 13 is named as boron family, group 14 carbon family, group 15 nitrogen family, group 16 oxygen family, group 17 halogens, and group 18 are noble gases. You can see the other families are there: nitrogen, phosphorus, arsenic, antimony, bismuth, then oxygen, sulfur, selenium, tellurium and polonium, then fluorine, chlorine, bromine, iodine, actinium, and then you can see helium, neon, argon, second krypton, xenon and radon. Okay, what about helium? We will be discussing in the next sessions. Okay, so today we are covering these boron and carbon family. So let's begin with the session. You can see the general electronic configuration of each and every element in case of boron family. You can see in boron family we have in 13th group boron, aluminium, gallium, indium and thallium. Okay, there are five you can see elements that we are discussing. Okay, so you can see boron atomic number is 5, aluminium 13, gallium 31, indium 49, thallium 81. You can see the electronic configuration of boron is helium, then 2s2 2p1. Then I am not discussing the other one. I am just seeing you can see just 3s2 3p1, 4s2 4p1, 5s2 5p1 and 5d10 6s2 6p1. I am not discussing the initial electronic configuration. I am just discussing the valence electronic configuration, right? You can see here the valence shell is second, valence shell is third, valence shell is fourth, valence shell is fifth, valence shell is sixth. So if the period number is increasing, you can see this belongs to second period, this is third period, fourth period, fifth period and sixth period. So definitely 2s2 2p1, 3s2 3p1. So the last shell electrons are the number of last shell electron is only 3 in each case. You can see 2s2 2p1 3, you can see 3s2 3p1 3, 4s2 4p1 3, 5s2 5p1 3, 6s2 6p1 3. That means what you can say, we will be discussing with the help of these valence shell electrons some properties. Okay, so let's begin with the periodicity and properties of p block elements. This is going to be very interesting. Periodicity and properties of p block elements. You can see what are p block elements. The first part is here, what are p block elements. As I already told to you in our periodic table, right? Periodic table 118 elements are properly organized, right, and properly well settled. Those and not each and every element is well settled, right? But in our this periodic table we are discussing we have 118 elements, and 118 elements have been discovered so far. So you can see here in periodic table, in this periodic table there are 4 blocks, as I already told to you. So the p block elements are located on the right hand side of the periodic table, starting from group 13 boron family to group 18 noble gases, right? These elements have valence electrons in the p orbital. That's why these elements are named as p block elements. Okay, next point. The p block elements includes metals, non-metals and metalloids. That's very interesting part. P block elements includes metals, non-metals and metalloids. Very interesting. They exhibit a wide range of chemical properties and react with other elements to form various compounds, right? To form various compounds. So in p block na, we have metals, we have non-metals and we have metalloids. So elements are classified actually in 3 categories: metals, non-metals and metalloids. And in p block each and every type of elements are there. Okay, now the next point you can understand periodicity, atomic size and ionization energy. So we are discussing these 3 points now. So the properties of p block elements show periodicity. Periodicity means like variation in a regular pattern, right? You can see they vary in a regular pattern across a period and down a group. For example, we have a clock and this is the clock pendulum, right? So this is going in 1 second here, then in another 1 second here. Okay, so this is going in 1 second, then 1 second to come back, then 1 second to go here, then 1 second to come back. Similarly, so it is taking, this is called repetition process, this is called periodic process, right? So this is periodicity. So repetition in period what I can say, properties in a regular pattern in case of periodic table, in case of elements, that is known as periodicity, right? If we are moving across a period in a periodic table or we are moving down a group in a periodic table. The atomic size of p block elements decreases. What I want to say, the atomic size of p block elements decreases across a period and increases down a group. As you know that, suppose I am comparing boron, carbon, nitrogen, oxygen, fluorine, etc. So we are moving left to right. Boron, carbon, boron atomic number 5, carbon atomic number 6, nitrogen 7, oxygen 8, fluorine 9. Okay, so what is happening here? The number of protons and number of electrons are increasing, but the interesting part is here, if I am writing the normal electron configuration in terms of KLMN, so the electron configuration is 2 3, then 2 4, then 2 5, then 2 6, then 2 7. The interesting part, that in each case only 2 shells are there. In each case only 2 shells are there. In each case only 2 shells are there. So if only 2 shells are there, that means the number of shells are fixed, but the number of protons and electrons are increasing. So what is happening? The shells, the outermost shell is coming closer and closer to the nucleus due to attraction, right? So due to increase in Z effective, that means you can say due to the increase in effective nuclear charge, due to the increase in effective nuclear charge, the outermost shell comes closer and closer to the nucleus, and size decreases, and size get decrease. Okay, so you can see if we are moving across a period, so due to increase in effective nuclear charge, size decreases, but down a group, top to bottom, size increases because z effective increases, we know, but the addition of new shell dominate the effective nuclear charge. So if there is an addition of new shells, if we are jumping from second period to third period, third period to fourth period, so definitely what happens, definitely size will increase. Okay, so the addition of new shell will dominate every part. Okay, the ionization energy generally increases across a period and decreases down a group. Ionization energy is nothing, that is the amount of energy required to remove the electron from its outermost shell of an isolated gaseous atom. So suppose we want to remove an electron, and you know very well fluorine size is less as compared to boron. Okay, so that means the outermost electron, suppose this is boron nucleus, and this is the last shell of boron, and this is the electron of boron. Okay, and suppose this is the distance 10 in units. Okay, then this is the nucleus of fluorine, and this is the last shell of fluorine, and this is the electron, one of the electron of this 7 electrons. Okay, then this distance is what, suppose this distance is 7. So there is a more attraction between the nucleus and the last shell electron, and as compared to fluorine, less attraction is here, right? So if electrostatic attraction is less in case of boron as compared to fluorine, definitely it is easy to remove this last shell electron from this boron isolated gaseous atom as compared to fluorine. That means we have to provide less energy, it requires less energy to get removed, but it requires more energy, right? So definitely the point says that due to increase in effective nuclear charge across a period left to right in a periodic table, atomic size decreases and ionization energy increases, because we have to supply more and more amount of energy if the nucleus and last shell electron attractions are more. Okay, okay, so the ionization energy generally increases across a period and decreases down a group. So what you can write now, z effective is effective nuclear charge. So z effective is what, if z effective increases, size decreases. So z effective is inversely related to size. If z effective decreases, size increases, right? Okay, and if z effective increases, size decreases, definitely size decreases. If size decreases, ionization enthalpy increases. That means if z effective increases, size decreases, and ionization enthalpy increases. That means z effective is like is directly related to ionization enthalpy. If z effective is more, we need to supply more amount of energy to remove that particular electron from its last shell, right? From its outermost shell of an isolated gaseous atom. That is about the 3 points: periodicity, atomic size, and ionization energy. I hope you are very much clear. Let's move to the next point. The next point is electronegativity and metallic character. Okay, so if an element lose electron with more easiness, definitely it will have more metallic character. Okay, and electronegativity, it is nothing, it is like a tendency and to attract the shared pair of electrons toward itself. So it increases across a period and decreases down a group, because across a period if you are moving left to right, definitely size decreases, jet effective increases. So attraction part, that means the nucleus hold towards the shared pair of electrons will increase, right? So definitely nucleus will attract the shared pair of electron more quickly as compared to the left one. You can see here, suppose I am comparing boron, carbon, nitrogen, oxygen and fluorine. So fluorine is more electronegative as compared to oxygen, nitrogen, carbon and boron, because if you are moving left to right, size decreases, right? Z effective increases. Due to increase in Z effective, that means the attraction power of this fluorine nucleus will increase, and it can attract the shared pair of electrons, right? Shared pair of electrons more easily as compared to oxygen, nitrogen, carbon and boron. Now the next point is the metallic character decreases across a period. Let's go back to the electronegativity point. Electronegativity increases across a period when you are moving left to right in a periodic table, but it decreases down a group, because down a group size increases, right? because down a group size increases. Let's go back to the metallic character point. So metallic character decreases. You know very well, if size decreases, that means the electron, outermost shell electrons and the nucleus hold is more. If hold is more, so it is not easy to remove that particular electron, so that particular element will not lose electrons easily. And if the loss of electron is not an easy task, so definitely metallic character will decrease. So you can say with the size decrease, metallic character also decrease and non-metallic character increase. So I am summarizing the points. Left to right, Z effective increases, ionization enthalpy increases, size decreases. If size decreases, metallic character decreases. If metallic character decreases, non-metallic character increases, because acceptance of electrons will increase. Acceptance of electrons will increase. And if you are moving top to bottom in a group, size increases, Z effective also increase, right? But the addition of new shell will dominate the Z effective part. Okay, and also the electron number of electrons are increases in outermost shell, and definitely so electronic repulsion will also increase. Okay, the main point is here, top to bottom size will increase, so ionization energy will also decrease, not increase. Okay, so if size increase, ionization energy decreases. If size decrease, ionization enthalpy increases. Okay, now the interesting part is here, metallic character top to bottom will increase. Okay, left to right across a period, metallic character decreases, and top to bottom metallic character increase. Okay, okay, let's top to bottom down group. Okay, it increase. Let's move to the next group 13. Let's begin with the group 13, boron family. Boron family, in boron family we have boron, aluminium, gallium, indium and thallium. Okay, we are discussing these elements. So group 13 elements include boron, aluminium, gallium, indium and thallium. These elements have 3 valence electrons in its valence shell. You have seen the electronic configuration of each and every element in a tabular form, right? Let's move to the next point. Boron is known for its ability to form covalent compounds. Okay, it can form BCl3, it can form BH3, etc. It can form these types of compounds. Aluminium is widely used in various industries due to its lightweight and high strength. Let's move to some important reactions. Some important reactions of boron. You can see this is boron. When it will react with X2, X2 is like a halogen. Okay, so it can form BX3, like it can form BF3, it can form BCl3, it can form Bi3, etc. Okay, BBr3, etc. Okay, metal M. When boron reacts with a metal, it will form MXBY type compound. It will form MXBY type compound. Okay, okay, let's move to the next. Boron when react with oxygen, it will form boron oxide, which is a B2O3 type oxide, B2O3. When boron reacts with a base, it will form Na3BO3. It will form Na3BO3 and release of hydrogen gas will take place. When boron react with sulfur, when boron react with sulfur, so you can see here it will form, but it will form a compound, that is what, boron sulfide B2S3 type. Okay, when boron react with MH3 type, okay, MH3 metal hydride, so it will form Bn. When boron react with NH3, this is ammonia, so it will form Bn plus H2. And when boron reacts with nitrogen, it will form Bn type compound. And when boron react with nitric acid, it will form S3BO3, right, S3BO3, which is boric acid plus nitrogen dioxide. This is boric acid, and sometimes this boric acid is written as like BOH whole thrice, like this. Okay, so this is all about the chemical reactions of boron. So let's discuss some questions. Some important questions are there from group 13. So you can see group 13 questions are there. Question number 1, why is BCl3 more stable than TLCl3? Why is BCl3 more stable than TLCl3? If you can see here boron, then gallium, then indium, then thallium. That means you are moving top to bottom in a group. Top to bottom in a group, we know that ionization energy decreases, size increases, right? Size increases, ionization energy decreases, and metallic character also increases. So if you are moving top to bottom, what happens? Due to inert pair effect, right? So you can see the answer. Answer, BCl3 is more stable than TLCl3 because in boron 2s2 2px1. This is the last shell electron configuration. Simply you can write 2p1, no problem. All 3 valence electrons are available for bonding with chlorine because you know, due to shielding effect. Okay, I will discuss that point. While in TLCl3, like 6s2 6p1, that is the electron configuration, the 6s orbital experience a maximum screening effect because the screening effect, right, screening effect like a shield. Okay, what I can say, screening effect is like a shielding provided by the inner shell electrons, right, provided by the inner shell electrons to the outer shell electrons towards the effective nuclear charge or towards the nuclear charge. Okay, that's why the exact amount of nuclear charge which is present in the nucleus is not available for the last shell electrons or not available for the outer shell electrons. Okay, so what is happening here, due to the inner pair effect, the 6s orbital and the inert pair, that the shielding effect is more in case of S, the screen is more in case of S, then P, then D, and then F. Okay, because in case of 6s and 6p, F and D are included. So what happens, because they have less screening and less shielding effect, so a 6s orbital experience a maximum screening effect. Thus only 6p, one electron is available for bonding with chlorine, and making BCl3 more stable than TlCl3, making BCl3 more stable than TCl3. So that is the reason behind this question. I hope you are very much clear. So 6s orbital electrons are not available for bonding. 6s orbitals electrons are not available for bonding. They experience a maximum, you can say screening effect means they experience a maximum attraction, right? And if they are closely attracted towards the nucleus, so that means they are not available for bonding. So that's why BCl3 more stable than TlCl3. And a simple generalization I want to say, oxidation state. The generally group 13 elements show +3 oxidation state. This is the general oxidation state of group 13 elements. But top to bottom, the stability of +3 oxidation state decreases and +1 oxidation state increases. Okay, so that's the point here. Let's move to the next question. Which of the following statements about S3BO3, I told you S3BO3 is named as boric acid. Okay, and it is also written as BOH whole thrice. Okay, is not correct. So it is a strong tribasic acid. It is prepared by acidifying an aqueous solution of borax. Okay, borax is nothing, that is Na2B4O7.NH2. I will discuss. It has a layer structure in which planar BO3 units are joined by hydrogen bonds and does not act as a proton donor but act as a Lewis acid by accepting hydroxyl matlab OH negative ions. Okay, means OH negative ions. So let's discuss the solution. The correct options, you can see the B is one is the correct option. It is prepared by acidifying an aqueous solution of borax. Borax is Na2B4O7, and when it is acidified, that means reacted with HCl plus 5H2O, you will get 2NaCl plus H3BO3. So you can see boric acid is prepared here. Then you can see it has a layered structure in which planar BO3 units are joined together by hydrogen bond. You can see here B O O O BO3, and you can see hydrogen bond, hydrogen bond, hydrogen bond, like this. So they are attached. This is the layered structure of S3BO3 units. Okay, the next one D. It does not act as a proton donor as it acts as a Lewis acid by accepting a lone pair hydroxyl ions. Okay, so it is not a protic acid but it acts as a Lewis acid by accepting electrons. So Lewis acid means electron pair acceptor and Lewis base means electron pair donor. You can see BOH whole thrice plus 2H2O, it will can form BOH whole 4 negative plus H3O positive. So B, C, D are correct, and option A is incorrect. Okay, hence the correct answer is option A. So it is not a tribasic acid. It is not a tribasic acid. Let's move to the next one. Next question is saying that the Lewis acid character of boron trihalides follows the orders. Okay, I hope the previous answer is clear to all of you. Which of the following statements about H3BO3 is not correct? So the answer is A. It is a strong tribasic acid. That is not correct. Okay, that is not correct. So let's move to the next. Next one is very simple. The Lewis acid character. Lewis acid means electron pair acceptor character of boron trihalides follows the order Bi3, BBr3, BCl3, and BF3. That means these are boron halides. So boron is same, but the size of fluorine, chlorine, bromine, and iodine is changing. Okay, the electronegativity value is changing, the ionization energy value changing. So let's understand the answer of this particular question. So you can see here the solution. As extent of back bonding reduces down the group, you know very well, extent of back bonding reduces down the group because back bonding will takes place in that particular orbitals which are of same energy. That means boron electronic configuration, boron atomic number is 5, electronic configuration is 1s2, 2s2, 2p1, right? And fluorine electronic configuration is 1s2, fluorine atomic number is 9. So 1s2, 2s2, 2p5. That means both orbitals 2p and 2p, right? Both are of same energy level. So in 2p, the overlapping is very good, right? The overlapping extent is good. So extent of back bonding is more in case of boron 2p and fluorine 2p. But here 2p, and here 3p. So overlapping is not effective. So 2p and 4p, 2p and 5p. So in these cases the overlapping region will decrease. If the extent of back bonding is less, definitely what happens? What happens? You can see as extent of back bonding reduces down the group, leading to more Lewis acidic strands. So that's all about the answer of this particular question. Let's move to the next. The correct order of basicity of oxides of vanadium. So this belongs to the oxidation state: V2O3, V2O5 and V2O4. You can see here V2O3. So if you want to calculate the oxidation state of vanadium, so you can assume X. So you can write 2X, and for oxygen it is -2, 3 is 6, and equal to 0, X will be +3. For V2O4, it comes out to be 2X -8 equal to 0, X comes out to be +4. For V2O5, 2X -10 equal to 0, X comes out to be +5, right? So +3, +4, +5, that means oxidation state increases. So what will be the order now? So let's see the solution of this particular question. As a positive oxidation state increases, so here it is +3, here it is +4, here it is +5. Acidic nature increases and basic nature decreases. If the positive oxidation state increases, so acidic nature also increases, but basic nature will decrease. So what should be the order? V2O3, then V2O4, then V2O5. So V2O5 is the least basic, and this is the least, and this one is the most, okay, among these. Let's move to the next. Let's discuss the group 14 elements. Group 14 elements, and you can see first of all the electronic configurations of group 14, each and every element. Okay, so you can see in group 14 we are discussing carbon, silicon, germanium, tin and lead. Okay, the symbols are carbon C capital C, silicon capital S small I, germanium capital G small e, tin SN capital S small n, and lead PB, that is capital P and small b. Atom number 6, 14, 32, 50 and 82 respectively. What will be the electronic configuration? If you will write the electronic configuration according to the what rules that we had discussed already in structure of atom, that means Above principle, Hund's rules and Pauli's exclusion principle, you can see the electronic configuration will come 2s to 2p2 for carbon, right? I am discussing only the last shell electronic configuration. 3s to 3p2 for silicon, 4s to 4p2 for germanium, 4d10, 5s to 5p2 for tin, and 4f14, 5d10, 6s to 6p2 for lead. That means the general electronic configuration for carbon family is ns2 and p2. For the general electronic configuration for entire p block is ns2 np 1 to 6. The general electronic configuration for boron family is ns2 np1. The general electronic configuration for carbon family is ns2 np2. That means the general oxidation state of carbon family is +4, right? So let's discuss the next point. First of all, I want to discuss low atomic mass, metalloid nature and low reactivity. So let's discuss something about boron as well. Boron is a member of group 13, also known as the boron group. Okay, on the periodic table exhibits some unique behavior. So what is the unique behavior of the boron element in the 13th group? Then we will be discussing the 14th group. Okay, so first point is here low atomic mass. So you can see here boron is the lightest element in group 13 with an atomic number of 5. Its low atomic mass result in unique chemical and physical properties. What about metalloid nature? Boron is classified as a metalloid, which means it possesses some properties of metals and some properties of non-metals. It exhibits some metallic properties like high melting point, electrical conductivity, also non-metallic properties like brittleness and low reactivity. Then you can see before that I want to discuss one more point, that is the point 3. The point 3 is very simple, that is what about low reactivity. Boron is less reactive. Boron is less reactive than other elements in group 13 such as aluminium, gallium, indium and thallium. It forms a protective oxide layer on its surface which makes it resistant to corrosion and oxidation. Similarly, aluminium can also form protective oxide layer like this. Okay, so let's move to the point number 4. High melting point. Boron has a high melting point of around 2076 degrees Celsius, which is higher than the most other elements in its group. This high melting point is attributed to the strong covalent bonds present in its crystal lattice. So what is the conclusion here? Boron can form covalent bonds, that means due to the sharing of electrons, and the fifth point is wide range of allotropes. Boron exists in several different types of allotropes. Allotropes you know very well, same element but different physical properties, right? So different types of allotropes are there, meaning it can form different structural arrangements. Some common allotropes of boron include, like you can see, amorphous boron, crystalline boron, and boron nitride. Okay, each possessing distinct physical and chemical properties. Sixth point, unique bonding characteristics. So boron forms strong covalent bonds and can form a variety of what? Variety of compounds with other elements. It's commonly forms compounds with hydrogens are boranes, okay, and carbon are boron carbides, which have diverse applications in industries such as energy storage, aerospace, and electronics. So this is the uniqueness of boron. So basically boron has small size, high electronegativity among all elements, okay, and electronic configuration, right? So these are some points, okay, these are some points of boron, right, and due to which it shows unique nature, unique behavior apart from other elements. Let's go to the group 14 carbon family. Group 14 elements includes carbon, silicon, germanium, tin, and lead, and you know very well the group 14 electronic configuration, general electronic configuration is ns2 np2. The carbon family general electronic configuration will be ns2 np2. Now the my point is these elements have 4 valence electrons, okay, you can see ns2 and np2. Carbon is unique and forms the basis of organic chemistry. In organic chemistry now you can see here, so in organic chemistry basically we have to study carbon and hydrogen, right? Carbon and hydrogen compounds, and with some other elements like oxygen, nitrogen, fluorine, sulfur, okay, with some other heteroatoms as well. So main atoms are like carbon and hydrogen. Like you can see the simplest hydrocarbon is CH4, then C2S6, right, etc, like this, okay, methanol, ethanol, methanol, propanol, like this. Silicon symbol is capital S, small I. Silicon is a semiconductor, and semiconductor is widely used in electronic devices, right? So that's all about the group 14 elements carbon family. Now we are going to discuss some reactions as well, but before that I want to write some point of about tin and lead. So tin symbol is Sn and lead symbol is Pb. So tin and lead are metals with low melting points, okay, these metals have low melting points, so you can see these are like soft metals. These elements show a trend in physical properties such as increasing melting and boiling point down the group. If you are moving top to bottom down a group, the melting point and boiling point will increase. The melting point and boiling point will increase. Let's move to the chemical properties and physical trends of group 14 elements. So the point is here, carbon forms a varieties of compounds, like it can form CH4, it can form CO2, it can form CaCl4, it can form CCl3, etc. So carbon can form, it can form CaCl3. It can form variety of compounds due to its ability to form stable covalent bonds. Carbon has its unique nature due to three properties like tetravalency. Next one is like what? Tetravalency, and we will be discussing the other two properties as well. So carbon is unique element. Carbon is a unique element. Tetravalency, small size, and catenation. These are the three properties. These are the reasons of the uniqueness of carbon. Okay, these three properties are the uniqueness of are the reasons for the uniqueness of carbon. Next one is silicon. Silicon forms compounds similar to carbon but with different properties. And the next one is germanium. Germanium symbol is Ge. Germanium, tin and lead. Tin symbol is Sn, lead symbol is Pb. Okay, less reactive compared to carbon and silicon. So more reactive in case of carbon family are carbon and silicon. So what you can say, if you are moving top to bottom down a group, reactivity will decrease. The boiling point and melting point of these elements increases down the group due to increase in London dispersion forces, because if you are moving top to bottom down a group, size will increase as well as molecular mass will increase. So that's the reason behind this. Okay, these elements can form both positive and negative oxidation state. That's very interesting point. That's very interesting point. Okay, these elements, carbon family elements, that means carbon, silicon, germanium, tin, and lead, can form both positive and negative oxidation state. Now my point is here, silicon. Okay, we have discussed about carbon. What about silicon? Silicon reacts with oxygen to form silicon dioxide like SiO2. Carbon reacts with oxygen to form carbon dioxide like CO2, right? Can react with halogens to form silicon halides like SiCl4. Carbon reacts with what I can say halogens, like it can form carbon halides like CCl4. Can form various organosilicon compounds. It can form various organosilicon compounds. Let's move to the tin. Tin symbol is SN. SN reacts with the oxygen to form SnO2, which is tin oxide. It can undergo redox reactions to form tin 2 compounds like SnCl2. It can form tin chloride. It can react with acids to form tin salt. It can react with acids to form tin salts. Now the next and interesting point is here, that is about lead. Lead is nothing, that is a symbol Pb due to its Latin name, which is plumbum. Due to its Latin name, which is plumbum. Lead can react with oxygen, similar like carbon, silicon and germanium. Okay, similar like carbon, silicon, germanium, tin and lead. So it can form what? You can see it can form lead oxide, which is PbO. It can react with halogens to form lead halides like PbCl2. Okay, and it can form it can undergo redox reactions to form lead 2 compounds. Okay, like PbSO4. So these are some what? These are some lead 2 compounds. Now let's understand some important reactions of carbon, and then we will be discussing the unique behavior of carbon from other elements. So important reactions like combustion reactions. So C plus O2 gives CO2. When carbon is burning in presence of oxygen, it will form CO2 along with the release of heat as well plus water, right? So this is like combustion reaction. Suppose you are burning any hydrocarbon which is an alkane. So CnH2 and plus 2 is an alkane, and it reacts with oxygen. And what will be the balanced chemical equation? You can learn this: 3n plus 1 by 2 O2. It will give NCO2 and n plus 1 H2O plus heat, n plus 1 H2O plus heat. So this is going to be very interesting, and you have to learn these points. Suppose I am writing CH4. CH4 will react with how many carbon? 1 2 3. 3 plus 1 4. 4 divided by 2. CH4 plus 2O2 gives CO2 plus 2H2O. Now you can see this is the complete balanced chemical equation, and this is the combustion reaction of methane. This is the combustion reaction of methane, like this you can understand. Now the next point is formation of carbon halides. So if carbon reacts with halogen, it can form carbon halides like CCl4, like CBr4. It can form carbon tetrachloride, carbon tetrabromide, etc. So this is about the formation of carbon halides. Now the next interesting point, reaction of carbon with hydrogen. It can form carbon hydrates, or you can say hydrocarbons, like it can form CH4, it can form C2H6, it can form C3H8, it can form any other hydrocarbon, etc., right? So basically carbon and can react with hydrogens, and it can form what? Hydrocarbons. It can form hydrocarbons. Next one is reaction of carbon with sulfur. Formation of carbon sulfide. So when carbon reacts with sulfur, you can see C plus 2S gives CH2. It can form carbon disulfide, guys. Just carbon reacts with oxygen, it can form carbon dioxide. It can form carbon dioxide. Similarly, carbon reacts with sulfur, it can form carbon disulfide. It can form carbon disulfide. Next reaction is formation of cyanides or isocyanide. When carbon reacts with nitrogen, it can form cyanogen. This cyanogen can be written like CN whole twice. When carbon reacts with nitrogen, so 2C plus N2 gives C2N2. So it can form cyanogen. Now the next interesting point, formation of carbides. Carbon react with metal, it can form metal carbides. It can form metal carbide where M is a metal. So now you can understand formation of covalent bonds, allotropes and organic chemistry, right? So this is the unique behavior of carbon. This is the unique behavior of carbon element in 14th group. This is the unique behavior of carbon element in 14th group. So carbon, a member of group 14 on the periodic table. On the periodic table, you can see here exhibit several unique properties or unique behavior compared to what? Compared to other elements in its group. Compared to other elements in its group. The first point is here, formation of covalent bonds. Easily carbon can form covalent bonds. So carbon is known for its ability, you know very well. Covalent compound, covalent compound, covalent compound, covalent compound. So these are covalent compounds. So carbon can form covalent compounds. It can form covalent bonds. It is known for its ability to form strong covalent bonds with other elements, including itself. This ability allows carbon to wide variety of compounds, to form wide variety of compounds due to small size, due to tetravalency, and due to catenation. Carbon can form wide variety of compounds, and you can see it can form wide variety of compounds, as well as what it allow due to these three properties, carbon can form wide variety of compounds, and it can form large and complex structures as well, okay, ranging from simple hydrocarbons to complex organic molecules. Okay, let's move to the allotropes. Allotropes, carbon has the ability to exist in different forms, okay. Same element but different forms are there. So different elements like allotropes are there, like graphite, like fullerene, like diamond, which are different forms of the same element with different physical and chemical properties. Different physical and chemical properties, like graphite is soft but diamond is hard, but made up of same element, which is carbon. That's the point here, okay. Some examples of carbon allotropes, as I told you already, some examples of carbon allotropes are diamond, graphite, and fullerene. Fullerene is like a buckyballs and nanotubes, okay. Next one is organic chemistry. As I told you already, carbon is the like backbone of organic chemistry, right? So in organic chemistry we have to study majorly carbon and hydrogen compounds. So carbon is the cornerstone of organic chemistry, as it is the basis for all living organisms and the compounds they produce, like in our DNA, in proteins, in vitamins, like in mostly things carbon is present. In our food, in our clothes, in mostly things carbon is present. In sucrose, glucose, in proteins, vitamins, in these things, what is that? Carbon is present. So what I can say, and the compounds they produce. It has a unique ability to form long chains, as I told you already, due to the uniqueness of carbon. Carbon can form long chains and rings along for the vast diversity of organic chemistry, along for the vast diversity of organic chemistry found in nature, organic compounds found in nature. Now the next and interesting point number 4, carbon dioxide fixation. Carbon has a unique ability to fix carbon dioxide from the atmosphere through photosynthesis process. Photosynthesis process, you know very well, like plants undergo photosynthesis process. This process is crucial for the production of glucose, right, and other organic molecules that serve as energy source. For what? For living organisms. Now the next and fifth point is here, carbon based materials. Carbon based materials have exceptional properties. Like what are the exceptional properties? Like high strength, right, they have low density, you can say they are good electrical conductors, okay. This makes carbon based materials more unique, like cotton fibers and graphene high valuable, more valuable, right, in various industries, including aerospace and electronic industry. Now the next and interesting point is here, question. So let's discuss some important questions for JEE exam. Question is here, like a 10 liter of a mixture of CO and CO2 gas is passed over heated coke when volume increases by 2 liter. What is the percentage composition of the mixture? So CO and CO2 gas mixture volume is 10 liter. If CO is X, so CO2 will be 10 minus X. It is passed over heated coke, then volume increases by 2 liter, so it becomes 12 liter now. So what is the percentage composition of the mixture? This is very simple question, you can see the solution. So CO2 when reacts with coke, you can see CO2 plus C, it will give 2CO. That means you can understand we are passing carbon monoxide and carbon dioxide, right, over the heated coke. So what happens? CO2, which is carbon dioxide, you can see here na, over the heated coke. So carbon dioxide can react with carbon is coke, okay, and when it is heated it can produce again carbon monoxide. That means carbon dioxide, we are taking carbon monoxide and carbon dioxide further converting itself into carbon monoxide. Carbon monoxide is already we have, okay. So what is happening here? CO2, suppose X liter in the initial mixture, we have 10 liter mixture of CO2 and CO. If CO2, carbon dioxide, is X liter, so CO will be 10 minus X liter. CO due to passes over heated coke, right, becomes 2X. How becomes 2X? From CO2, right, from CO2, because if we are taking 1 mole of CO2, so we are getting 2 mole of CO. If we are taking 2 mole of CO2, we are getting 4 mole of CO. If we are taking X mole of CO2, so we are taking 2x, we are getting 2x mole of CO. So x liter will convert itself into 2x of CO, right? So 2x we are getting from CO2, no effect on CO because CO is already in the mixture, right? So what is the final volume of CO? You can see CO already it is 10 minus x, okay, already it is 10 minus x plus what will be the next point, that is 2x. So 10 minus x plus 2x will equal to 12. So it becomes 2x minus x, 10 plus x equal to 12. So x comes out to be 2 liter. X comes out to be 2 liter. That means if you want to calculate the percentage or value, so if x is 2 liter, that means CO2 is initially 2 liter and CO is 8 liter. CO is 8 liter. That means if you want to calculate the percentage initially, so 2 out of 10, 2 out of 10 into 100, it comes out to be 20% for CO2, and 8 out of 10 into 100, it comes out to be 80% for CO, right? And if you want to calculate like 100 minus 20, then you can also calculate by using this method. Let's discuss the next question. The covalency and oxidation state respectively of boron in BF4 negative are. So you can see BAF4 negative, boron tetrafluoride anion, right? Boron is bonded to 4 fluorine atoms through covalent bonds. Therefore, the covalency of boron in its ion is 4. Covalency is 4. What is the oxidation state? That is very simple. If you want to calculate the oxidation state of BF4 negative, you have to assume that boron oxidation state is X. Then fluorine is -1. -1 into 4, -4 equal to -1 due to overall charge. So X comes out to be +3, right? So you can see the oxidation state of boron can be calculated by considering the charges on the atoms involved in the anion. Fluorine has an oxidation state of -1 and there are 4 fluorine atoms in the anion, so which contributes a total of -4 charge. Since the overall charge on the tetrafluoroborate anion is -1, the oxidation state of boron must be +3 in order to balance the charges. So the covalency is what? Covalency is 4 and oxidation state is 3, 4, BF4 negative. Okay, let's move to the next question. Next question is the incorrect statement from the following for borazine. What is this borazine? Borazine is like an inorganic benzene. It is like an inorganic benzene. Do you know organic benzene? Definitely we know organic benzene. Organic benzene has formula C6H6 and this will be the structure of organic benzene like this. Okay, so you can put, there are 6 carbon atoms, right? So you can put alternate boron and nitrogen and you will get inorganic benzene, right? And nitrogen will attach to one hydrogen atom. So you can see borazine formula is B3N3S6. Is an inorganic compound with a structure similar to benzene. When 3 boron and 3 nitrogen atoms form a hexagonal ring, boron, nitrogen, boron, nitrogen, boron, nitrogen, you can see they will form an hexagonal ring. Okay, 3 boron and 3 nitrogen atom will form an hexagonal ring. Okay, and you can see with altering single and double bonds. Okay, double, single, double, single, double. Okay, and a hydrogen atom attached to each boron and nitrogen atom. So let's attach each boron and nitrogen atom with a single hydrogen. So you can say this is B3N3S6. This one is known as what? This one is known as borazine. So borazine is hydrolyzed. Option A is what is saying that. What is option A? You can see it can react with water. So let's see. It can react with water. Borazine is hydrolyzed by water to form boric acid, ammonia and hydrogen. So this statement is correct. Okay. Option B, it is a cyclic compound. Yes, it is a cyclic compound. It's like an inorganic benzene. It has a hexagonal ring structure making it cyclic compound. So this statement is also correct. It has electronic delocalization. Definitely alternate single double bonds are there. So they can delocalize. The electrons in the boron nitrogen double bonds are delocalized over the entire ring, similar to benzene, like benzene. Okay. Next is option D. You can see it contains banana bonds, are typically used to describe the unconventional multi-center bonding in certain clusters or molecules. Okay, this is the delocalization. Okay, this is the delocalization. Bonding in certain cluster or molecules such as diboron B2S6. Borazine does not contain banana bonds. It has a planar hexagonal structure with alternating alternating single and double bonds. You can see alternating single and double bonds are there, and a simple hexagonal structure is this. Okay, this is not like a banana bonds. Okay, so you can see this statement is incorrect. Okay, so the incorrect statement is definitely it contains banana bond, option D. Let's move to the question next. Carbon has coordination number of 4 while other elements of this group have coordination number of 6. Why? Due to available d orbital in which n-1 p electrons can be excited to make coordination number 6, carbon lacks d orbitals. Okay, so in other elements now what happens, like suppose you are taking carbon and then silicon. Okay, so carbon atomic number is 6, silicon atomic number is 14. You can see 1s2, 2s2, 2p2, and in 2p no 2d is here, right? You can see in silicon 1s2, 2s2, 2p6, 3s2, 3p, 2p6, 3s2, 3p2, right? You can see in this case 3d is also available. In this case you can see 3d is also available, and it can jump electron from p or s to d, right, due to same what I can say, due to very less energy gaps, right, due to very less energy gaps. So what happens, due to this silicon can form 6 bonds. Okay, silicon can expand its valency beyond 4, and it can form coordination number 6 as well. It can form coordination number 6 as well. Okay, like it can form SiCl6. It can form SiCl6 as well. Okay, I hope this is clear. So this is very interesting about carbon and silicon, yes. For please you can ask your doubt. Okay, so carbon has coordination number of 4 while other elements of this group have coordination number of 6 due to this reason. Okay, so in case of what, carbon, d orbital is not present, but in case of other elements like silicon, germanium, tin and lead, d orbital is present. The next question is boric acid. Boric acid is nothing, that is S3BO3. Boric acid is called acid because its molecule contain H positive ions, gives a proton, accept OH negative ion which is hydroxyl ion from water releasing proton, combines with proton from water molecule. So why S3BO3 is named as boric acid? What is the reason behind this? So the reason is due to the small size of boron atom and presence of 6 electrons, boric acid accepts a pair of electron from OH negative ion, okay, which is hydroxyl ion. So acid means release of H positive or either accept of OH negative, right? If it is accepting OH negative and releasing H positive, definitely it can be as acid. Okay, if it is releasing H positive, it can be an Arrhenius acid. Okay, so boric acid accept a pair of electron from OH negative ion of H2O, thereby releasing a proton like this. Okay, that's the point here. So it can become what, it can be called as an acid. Let's move to the next question. Heating of an aqueous solution of aluminum chloride. Aluminum chloride is nothing, that is AlCl3, or to dryness will give AlOH Cl2, Al2O3, Al2Cl6 and AlCl3. Heating of an aqueous solution. If we are heating aqueous solution of aluminum chloride aqueous solution is acidic due to hydrolysis. So AlCl3 plus 3H2O, it will provide aluminum hydroxide. It will provide aluminum hydroxide plus hydrochloric acid. On strong heating, AlOH whole thrice is converted into Al2O3. So 2AlOH whole thrice upon heating, this is a delta symbol for heat, you will get Al2O3 which is aluminum oxide plus 3H2O. So this is the equation for this question. Next question. Boron cannot form which one of the following anions? Boron cannot form which one of the following anions? This is very simple. You can see coordination number 6 here, coordination number 4 here, coordination number 4 here, coordination number, you can see 2 oxygen atoms are attached together, right, attached here. So what is happening here? Which of the following anions are not possible in case of boron? So you can choose your answer. You can see boron atomic number is 5, electronic configuration is 1s2, 2s2, 2p1. As I already told to you, boron, in case of boron, I can write like this. Boron atomic number is 5, this is 1s2, electron configuration is 1s2, 2s2, 2p1. This is 1s, this is 2s. As you know very well, 1s has only two electrons. 1s can occupy maximum two electrons. 2s s orbital can occupy maximum two electrons, right? And this is 2p. This one is 2p. So let's fill the electrons. 1s2, 2s2, and 2p 1. So what will happen? What can happen? You can see here the electron from 2s, it can jump from 2s to 2p like this. This is the ground state, and you can see this becomes the excited state. This is 1 2, this is 1 1 2. Now the boron can form three bonds, right? This is the excited state. Okay, now boron can form three. So fourth lone pair is accommodated in this empty orbital. Maximum covalency is 4 in case of boron, right? And generally it can form three bonds. So due to the absence of 2d orbital, maximum covalency is 4 due to the absence of 2d orbital. Thus BF6 is not formed. Thus BF6 is not formed. Only condition number 4 is possible. Only condition number 4 is possible, like BS3 negative, BS3 plus H positive, like BOH whole 4 negative, like BOH whole 3. BOH whole 3 is nothing, that is boric acid plus OH negative, and BO2 negative are formed. Now the next question is, mark the oxide which is amphoteric in character. Amphoteric, so CO2, SiO2, SnO2, CO. Amphoteric means which can react with base. That means simply you can say amphoteric oxides are those oxides which can act as an acid as well as a base. That means it can react with an acid and it can behave like a base. It can react with a base and behave like an acid. Okay, which can behave like both acid and a base. Okay, so you have to choose the answer, and the answer of this particular question is SnO2, which is amphoteric in nature when it dissolves in acids as well as in bases, right? You can see SnO2 reacts with H2SO4. H2SO4 is nothing, that is a strong acid named as sulfuric acid. So SnO2 plus 2 H2SO4 gives SnSO4 whole twice tin sulfate plus 2H2. Then you can see similarly SnO2 can react with 2NaOH, right? It can react with 2NaOH. The next part is here, that is very interesting. Next question. Graphite is a soft solid lubricant, extremely difficult to melt. Okay, the reason for this anomalous behavior is that graphite is an allotropic form of diamond. It is an allotropic form of diamond, or it is an allotropic form of diamond, or it is made up of carbon element. You have to choose your answer. Has molecules of variable molecular mass like polymers. Has carbon atoms arranged in a large plates of rings of strongly bound carbon atoms with weak interplate bonds, and it is a non-crystalline substance. So there are four options A, B, C, and D. You have to choose your answer. You have to choose your answers out of these questions. Okay, everyone, and you have to complete these questions as a homework. You can see the next one. This is obtained when silica is heated at high temperature with carbon monoxide, carbon dioxide, or calcium carbonate. Carbon monoxide, carbon dioxide, and calcium carbonate, CaCO3. The next question you have to complete as an homework, that is as a homework, among the following substituted silanes, the one which will give rise to cross-linked silicon polymer on hydrolysis: R3SiCl, R4Si, RSiCl3, or R2SiCl2. The next question, name of the structure of silicates in which 3 oxygen atoms of SiO4, 4 negative, are shared is pyrosilicate, sheet silicate, linear silicate, or 3D silicate. Next, you have to complete the catenation tendency of carbon, silicon, and germanium. Carbon, silicon, and germanium is in the order germanium, silicon, and carbon. That means carbon has more catenating power, right? The bond energies in kilojoule per mole of carbon, silicon, and germanium bonds are respectively. So you have to use your concepts, and you have to do these questions. Okay, you have to complete these questions. Okay, these questions are in your homework. Next, identify the incorrect statement among the following. Ozone reacts with SO2 to give SA3. Ozone reacts with SO2, sulfur dioxide, and then you will get a product SO3. Is it true? You have to choose. Incorrect. Silicon reacts with NaOH, sodium hydroxide, in the presence of air to give Na2SiO3 and H2O. Cl2 reacts with excess of ammonia to give N2 and NH4Cl. Is it true? This type of questions, if you have what I can say, if you were more focused in your lower grades, definitely you can attempt these questions very easily, because Cl2 reacts with excess of ammonia. So what will you get? Okay, Br2 reacts with hot and strong NaOH solution to give NaBr, NaBrO4 and H2O. So you have to choose the incorrect. Okay, read the question very carefully, don't choose correct statement, you have to choose in this question incorrect statement. So this is the end of the session everyone. Thank you so much. I hope you find this session very well.